Welcome friends, Igor is here, and in this video we will work with the construction of a span of a finite set of vectors. In this lesson we will define the span of a finite set of vectors, learn to construct specific vectors in the span, and we will create a procedure which will allow us to check if any given vector belongs to a given span. Let's get started. The idea of a span is this. We are going to use a finite set of vectors to construct an infinite set of vectors, and we will use linear combinations to do this. Given a finite set of column vectors of the same size, their span is the set of all possible linear combinations of these vectors. So in these linear combinations the vectors are fixed, but the scalars are allowed to take any values. So, in this construction of a span, we start with a finite set of vectors and we use it to construct an infinite set of vectors, which is the span of the set. By the way, there is one exceptional case where the span is not an infinite set, it is a finite set. Can you find this exceptional case? Please let me know your thoughts in the comments down below, and I will do my best to respond to all your comments. Let's look at an example of a span construction. We are going to start with a set T, which contains 5 vectors of size 4. We are going to use this finite set of 5 vectors to construct an infinite set of vectors, which we call the span of T. The span of T consists of all possible linear combinations of the vectors from the set T. It is easy to construct examples of specific vectors from the span. For example, I can assign arbitrary values to the 5 scalars and I will compute the result of the linear combination, and this is an example of a vector from the span. We can do this again by simply choosing another set of scalars. See, the vectors remain the same. They are the given vectors from the set T. What we are free to change are the scalars in the linear combination. I can also construct the following vector. If you assign 0 values to all scalars, then notice that you will always get the 0 vector as a result of the linear combination. And in particular, this last example illustrates that the 0 vector belongs to every span. Now, constructing examples of vectors from the span was easy. What about the opposite problem? We are given a certain vector and we would like to know if this vector belongs to the given span. So let's take the same set of vectors T as in the previous example, and now we are given a specific vector U, and we would like to know whether this vector U belongs to the span of the set T. The vector U belongs to the span as long as it can be represented as a linear combination of the given vectors from the set T. In other words, we are asking if there are values of scalars alpha1 through alpha5 which make the linear combination of the vectors from the set T equal to the given vector U. Let's recall one of our previous results. We proved that solutions to linear systems are linear combinations of the columns of the coefficient matrix that is equal to the vector of constants. Therefore, we can think of solutions in terms of alphas for this vector equation as solutions to the linear system represented by the following augmented matrix. The way I constructed this augmented matrix is as follows. I used the column vectors from the set T as columns in the coefficient matrix and the given vector U as a vector of constants. To solve the linear system represented by this augmented matrix, we of course reduce this matrix using the Gauss-Jordan elimination algorithm. And we see that the linear system is consistent because the last column is not a pivot column. Therefore, it is possible to find values of scalars alpha1 through alpha5 which ensure that the corresponding linear combination of the vectors in T is equal to the given vector U. And in turn, this means the vector U is a member of the span of T. Let me also construct examples of explicit presentations of the given vector u as linear combinations of the given vectors from the set T. For this, we simply need to construct some specific solutions of the corresponding linear system. From the reduced matrix, we see that x3 and x5 are the free variables, and x1, x2, x4 are the dependent variables. So we have an infinite solution set, which can be described using two free variables. And now, to construct an explicit presentation of the vector u as a linear combination of the given vectors from the set T, all we need to do is to construct one particular solution of this linear system. And we can construct particular solutions by assigning specific values to the free variables. For example, what could be simpler than to assign zeros to the free variables x3, x5? This gives us an explicit presentation for the vector u as a linear combination of the vectors in T. Please check that the linear combination on the left-hand side simplifies indeed to the vector u. Let's do this again. We have the same set of vectors T, the same span, but now we're going to take a different vector v. Same question. Is this vector a member of the span of T? We follow the same approach. Effectively, we're asking if this vector equation has a solution for the 5 scalars. But the solution of this vector equation in terms of the scalars alpha 1 through alpha 5 is the same as the solution of the linear system with the following augmented matrix. When we reduce this augmented matrix, it turns out that the last column of the reduced row echelon form is a pivot column. This tells us that this linear system is inconsistent, it has no solutions. Therefore, it is impossible to express the vector v as a linear combination of the vectors in T, and this tells us that this vector v does not belong to the span of T. Let's summarize our today's findings. First of all, you saw that it is easy to construct specific examples of vectors from the span. You simply need to assign arbitrary values to the scalars and compute a specific linear combination. The last two examples showed that it is possible for some vectors to be in the span and for some other vectors not to be in the span. Moreover, the question of a membership of a given vector in a given span reduced to the question of consistency of a certain linear system. This linear system was constructed by using the vectors from the set T as columns of the coefficient matrix and the vector under question as a vector of constants. If you found this video useful, please give it a like to help others discover this content and subscribe to this channel to see future videos. In the next video in this series, we will find a connection between spans and null spaces of matrices. I will see you later.